Hey guys, so today we're going to be talking about 7.2, getting some introduction notes and kind of trying to understand the big idea here. So in 7.1 we talked a lot about exponential growth functions, and in 7.2 we're going to talk about exponential decay. Okay, so make that an A, exponential decay functions. So decay, what that means, okay, over time is that the value of our equation is going to decay or degrade to a set number or towards a set value. An example of a decay function would look like this. Y equals 1/2 to the x. In order for it to be decay, the number that has the exponent has to be less than 1. We call this value b. So it has to be less than 1. In the exponential growth problems, you would have noticed last time that they were always bigger than 1. And so here we're looking at something less than 1. And if we were to graph it, okay, we would start out with, if we put, do a little xy table, we know anything to the 0 power is by default 1. So 1/2 to the 0 power is 1. So I can put a dot right there, 0, 1. Anything to the first power is itself, like 2 to the first is 2, 5 to the first is 5. So 1/2 to the first power would be 1/2. So when I come over here to 1, I'm going to put a dot right at a half. It's a big dot, so bear with me. Now if I keep going to the right, okay, if I squared the 1/2, 1/2 times itself would be 1/4. So we can see this is going to get even closer to that axis. If we, however, go backwards and go to the negative numbers, let's remind ourselves that anything to a negative exponent is a reciprocation. It's going to produce a flipped fraction of 2 over 1. To the positive first, well, that's just 2, which means I'd come up here and put 2. If you remember the exponential growth functions from last time, you should be able to recognize that this is basically doing the exact opposite. Instead of starting flat and taking off, this one starts out very vertical and then flattens out over time. It's still going to have a horizontal asymptote right there at 0 for this problem. Still has the same domain and range restrictions that you saw in 7.1. So if that doesn't make sense, go back, watch 7.1, and come back to here. In terms of the domain and range, domain's all real numbers in the range, and this is y is greater than 0. Here's the deal with the decay. Okay, this is really important that we understand the difference between growth and decay. As we go to the right, okay, what's happening to the graph? And don't say that it's going down or that it's going up, because decay graphs can also look like this. Okay? This is also a decay graph. Both of these are decay graphs because as I go to the right, the graph is flattening out as it approaches a specific value. And it will get infinitely close to that value and not change again. Right? It's going to continue to get as close as possible, and it's going to continue to cut in half and half and half and half again, getting infinitely small towards that asymptote. Now if I put a +5 over here, okay, at the end of the problem, everything shifts up 5 spaces, and so the dotted line now would be at 5, and the graph would be dropping down and following 5. It doesn't matter that it's going to 0 or going to 5. What matters is that it is approaching that asymptote as we go to the right. Exponential growth problems from last time, okay, exponential growth problems started out on their asymptote and grew away from that value. Even when they were negative, even when we had negative growth problems, they would start out flat along the asymptote and then grow away from the asymptote. So those were our growth problems. Decay are all about approaching that asymptote as we go to the right. Now the application for things like this is really all over the place. One of the most common places you'll see this type of model here, we're talking about that half raised to the x, is what's called a radioactive half-life. Okay, half-life. The reason we care about things like that, everything from nuclear power production to nuclear waste management, which by the way, nuclear power management or power production is so productive and so powerful that it's always going to be part of how we approach energy production. But you know, how much uranium do we need, and how much of it's actually radioactive? Uranium does degrade into non-radioactive uranium over time. So we need to know how much do we actually have to gather, and how long is it going to be usable? Because after a while, it's no longer radioactive. So understanding its half-life, or when half of the material becomes stable and not radioactive, we need to know when that happens. And so understanding the radioactive half-life, it is an exponential decay graph. Things along those lines. All right. Hopefully that's enough to help you kind of get a sense of the difference between 7.1 and 7.2, growth versus decay, and you should be able to produce those graphs using calculators, Desmos, things like that. All right, good luck. We'll see you in class.